What do Nobel Prize-winning scientists, world-renowned artists, and 9-month-old Elizabeth here have in common? Quite a bit, really. We'll see that and more, this time on Science Without Walls. Have you ever watched a scientist at work? A real one, not the exaggerations or the caricatures you see in the movies. Let's observe a 9-month-old scientist at work. Elizabeth hasn't passed any courses, doesn't have many credentials, and of course receives no salary. But she's a scientist. She is trying to make sense of the natural world. She can't talk or directly ask questions of you and me. She couldn't understand our explanations or descriptions. But she can see, and yet we really don't know exactly what she is perceiving. She can certainly touch and feel, taste and smell. She is taking in all of that information and is trying to make some sense of the natural world. She is formulating simple hypotheses, testing, playing, experimenting, revising and testing and playing again. She is following the scientific method. She is not only taking in information via her senses, she is also processing that information and using it to control her output, her movements, her sounds. She's trying to decide whether to push or pull, cry or smile, crawl or stand still. We perceive the world through our senses. We touch it, taste it, smell it, hear it, see it, and feel it. Although there are some things we know because of our genes and genetic makeup, everything we know about the natural world has come in through our senses. Welcome to Program 2, Observing and Perceiving the Senses. You are here, still at the beginning. Your view of the world at this instant is not formed solely by what you are now seeing, hearing, or smelling. The information you are taking in is being processed, modified, compared, and evaluated. The result of all of that sensory processing and integration is perception. You have a perception of your world. I may perceive your world, your surroundings, very differently. To me, it might be hotter, brighter, louder, or more chaotic than it seems to you. We do not objectively sense the world. We non-objectively perceive it. Every time you sense something, learn something, experience something, your brain uses it, compares, evaluates, stores those experiences. And in the future, what you sense is compared, evaluated. Your entire sensory history is scanned before your brain decides on an appropriate, relevant, and useful perception. All of that history and experience is reflected in the billions and billions of connections between your brain cells, your specific neural wiring. Your neurons are interconnected, wired, but your wiring is not fixed. A future set of experiences, a new set of situations, and those connections may be modified. Your neural wiring is adaptable. Physiologists say it's plastic, meaning moldable or changeable. Elizabeth has kindly agreed to show us how she does science. She is operating on a partially clean slate, but she's highly motivated to learn. The connections she makes today will be used later in processing future sensory input and in providing appropriate output. You and I, however, have been neurally wired by 20, 30, 50 or more years of experience. One aspect of learning is forming new and revised connections between brain cells. Elizabeth is forming brain cell connections at an absolutely incredible rate, a rate far greater than you or me. The plasticity of our brain, its ability to develop new connections and to remodel old connections, its ability to wire itself in response to sensory input and experience, changes with age and with motivation. That's probably why young kids can learn a new language so easily, while you and I really have to work at it. There is some evidence that the rate of new connections decreases with age, although motivation can often compensate. Motivation is especially important. Leonardo da Vinci, the well-known 16th century artist, scientist, and inventor, said, "Just as eating against one's will is injurious to health, so study without a liking for it spoils the memory and retains nothing it takes in." You know what he means. We'll hear more from Leonardo later. Perception, the result of the processing of what you directly sense, is based on your experience and environment. That's why it is so incredibly important for babies, toddlers, young children to have positive sensory input. They need to be talked to, read to, sung to. They need to be touched, caressed. They need to have a wide range of experiences, of tastes, of smells. They need to see a wide range of images and colors and feel a range of textures. They need all of that information in order to develop their brain and to be able to respond to sensory inputs later in life.
What do you think that is? Her?
Cinderella.
Yeah.
You and I perceive the world through our senses. We may detect, receive, sense exactly the same information and perceive it differently, because perception is related to our experience, the wiring of our brain, and the circumstances at the instant we perceived it. Were you hungry? Was I tired, angry, happy? All of that influences how we perceive. In the words of Diane Ackerman, author of Natural History of the Senses and moderator of the Nova PBS series, The Mystery of the Senses, the world is a construct the brain builds based on the sensory information it is given. We have to understand our senses because if we rely upon them alone, uncritically and unquestioningly, they can fool us about what is really happening in the natural world. Scientists want a rational, objective view of the world. They don't want to sense some information one day when they are tired and the same information the next day when they feel much better, more upbeat, and perceive those two situations differently. Then we would be receiving the same information from good old Mother Earth and processing and perceiving it completely differently. In art, this can be very, very interesting, but it is simply not allowed in science. So both artists and scientists have to understand and control their senses, as well as their experiments. Sense control isn't a part of the scientist's training, but it should be. There is so much that you and I cannot see, hear, or smell. The information we take in is only a small part of all that is available. Both scientists and artists understand and realize the limitation of human senses. Scientists and engineers extend the senses. They build equipment, devices, machines, which allow us to sense the parts of the physical and natural world which we cannot naturally or easily sense. First, to sense something, we need a signal. We need something to sense. It could be light. It could be pressure changes in air. It could be various chemicals in the air. Second, we need a device to detect that signal. To measure it, we need a detector. But before it can be detected and measured, the signal has to get to the detector. It has to somehow make it from the source, where the signal was made or generated, to the device that is going to collect or sense it. It has to travel to the detector. The detector then detects it in some way. If that detector is one of your senses, then you sense the output of that detector. That output may be modified or otherwise processed before a signal goes to your brain. The appropriate area of the brain receives this signal, not the signal made by the source, but the signal that was translated, engineers say transduced, and processed in various ways so that the brain can deal with it. The brain only responds to light, for example, through the retina in your eye. No retina, no light detection. The brain responds to a certain range of pressure changes through the ears. No ears? Well, no or very little sensation of sound. All of our sensory organs are essentially appendages to the brain. They are devices, gadgets, pieces of equipment which nature has kindly developed, allowing us to receive information from the external, from the natural world. The information received, after some modification and processing, interacts and communicates with the internal world of our own brain. The brain takes these signals and evaluates them. It combines them in some way with your memory and history, and even with your genetic makeup, with your state of mind, your intention, your degree of concentration, and many other very poorly understood factors. You then have a perception based only in part on the physical signals you actually received. With that perception in hand, you now have some decisions to make. You have to decide what to do as a result of that perception. If you have sensed and perceived that someone is swinging at you, an action or response is initiated, probably to duck or to run or maybe to fight. If it's a signal from a dangerously hot object, you automatically and instinctively jerk back from the heat. This response generally occurs so quickly that you really haven't had time to think about it. It's an almost instantaneous reaction, an involuntary, instinctive response. But if you see an image or hear most sounds, you have time to process, to decide what you're going to do with that new information. You can detect light, you can detect pressure changes, you can detect chemicals, both in water and in the air. You can detect very small changes in weight or mass. You can detect what's up and what's down with respect to the gravity of the planet. Your brain and your sensory systems don't deal with senses individually. They deal with them collectively. We have the ability to take in the signals from all of our senses and process them together so that our perception is not due solely to sight input or solely to sound input or to smell signals, but it's due to all of them, all integrated, all connected together. How you do that is a very major area of study today. Your senses only sense exciting things. They sense change. If something isn't changing, you accommodate. Your senses adapt. Don't adjust your set. The buzz is intentional. There's a constant sound in the background. If it's there long enough and not too annoying, you will generally tune it out, so it doesn't bother you. Now, some of you can do that better than others. Some of you study to music. You find it relaxing or stimulating. Some of you may study to loud and perhaps even chaotic music. For some of you, that may even enhance your reading or viewing, where for someone else, that same music would dramatically distract from their reading or viewing. We are all different. Each of us is unique. My dad used to say, "It takes all kinds." Our senses have evolved to report changes. Something that startles has to be appraised or analyzed. What gets your attention are signals which change in time. The longer the signal is there, the less you worry about it. You perceive it less and less. It is only when it changes that your system really detects and processes it. Try to see an animal in the wild. Very difficult, unless it is moving. Sure, some of this is due to camouflage, but it is also due to the inability of your senses to perceive static signals. Remember the dinosaur scenes in the film Jurassic Park? If you are in front of a predatory dinosaur and you start to move, his senses respond. In the words of Diane Ackerman again, our senses crave novelty. Any change alerts them, and they send a signal to the brain. If there is no change, no novelty, they doze and register little or nothing. Let's use your sophisticated detectors, the built-in equipment by which you sense the natural world. The challenge is to calibrate them and use them effectively to observe and understand that natural world. First, your eyes. Pretend you're not watching TV. Pretend you're here in the studio with me, but with no TVs, videos, or cameras. Your eye collects photons. A photon is the word we use for an individual piece or chunk of light. The photons your retina has received have been reflected off of different surfaces, like this teddy bear. If the light is oriented differently, its reflections are different, and you see a different image. Later, we'll consider just how light is produced, how photons are reflected, and how they are absorbed or collected. For now, just assume that light, that photons, exist, produced by the sun or by some other light source, reflecting off surfaces and objects, some of them going into your eyes. The eye has an outer lens called the cornea. It also has a lens inside called the lens and a sensitive tissue, the retina, at the back. The cornea and the lens and the structure between them help process each individual ray of light, forming an image of the outside world on the retina. The retina absorbs some of those photons, producing signals which then make their way to the brain. Actually, it doesn't do this directly. It turns out that there are many signals from many different cells in the retina which are combined and processed. That processed signal is sent up to the appropriate visual part of the brain. Your eyes are not really like cameras. Yes, a camera has a lens. It can have a complex one, in many respects more complex than the lens in your eye. It has an iris, just as you do, which can be opened or closed in response to the amount of light available. And a camera has film, which absorbs photons, producing a chemical change. The change is made permanent by a chemical process called development. In a Polaroid camera, the chemical process is done very quickly. I've taken a picture of Scott, our cameraman. As the image develops, you won't recognize Scott until you see him in the flesh. The photographic film registers many of the photons it receives, but doesn't try to make sense of any of them. You can give it a nonsense pattern, and it will faithfully reproduce that nonsense image. Your eye doesn't do that. Your eye knows that there is a certain order to the natural world, and that certain things just don't make sense. You learned that as a baby, as a toddler, and that is now part of your neural wiring. If your eye gives you visual information that is completely inconsistent with the information you have received in the past, your eye and brain try not to confuse you. Your brain processes that information, compares it, looks up your history and memory, and tries to read into it what seems to make sense. What it provides for you after all that processing is your perception of that visual image. Here's Scott's partially developed Polaroid portrait. And here's Scott. Now that you've seen him, you can recognize his partially developed image. Here is an intentionally distorted photo. Because we have seen photos of the Mona Lisa before, this low-resolution image is interpretable to you and to me. You have enough information and experience to analyze and recognize this image. It makes sense. But now take an image of somebody or something you have never seen before and give that to your poor brain. It struggles to make sense of it, but it can't. We have to give your brain a higher resolution image. It accepts that as fact, stores it, and the next time you give it the fuzzy image, you recognize this fellow. It happens to be Joey, one of the production crew. Adios, Joey. Photographic cameras and TV cameras report images as they are. Cameras are objective. You are not, and neither am I. Some artists, great photographers, use this photographic objectivity to great advantage. It becomes their tool, their medium. A very big difference between your eyes and a normal still camera is that your eyes are designed for motion. They are not designed for static images. A camera is designed for static images. Video or movie cameras also make static images, but they make about 30 of them a second. Here's a strip of movie film. Single images hooked together in a long string. Take a set of images, change them ever so slightly from one to the next, figure out a way to show them to yourself quickly, and you have a movie like this. When you look at a scene, your eye actually collects the light for about 1/10 of a second and then sends that image on. Then it sends another image and another and another. Your brain puts all those images together to perceive motion. So if I show you individual images, each slightly different from each other, you see them individually. If I show them to you slowly enough. But if I show them to you much more rapidly, about 30 frames a second, you see dynamic images, movies, video. Your eye fuses those images into continuous motion, even though the videotape or movie film is just a series of static images. That's why animated Disney films work. Your sense of vision fools you into perceiving motion when it isn't really there. Your VCR works the same way, displaying a rapid sequence of images which you perceive as continuous. Play with the pause and jog keys on your VCR. The jog key moves one video frame at a time, just like the flip book. All of our senses are self-accommodating or self-adapting. You and I see and sense things differently because we are wired differently due to our different histories and experiences. But we also see and sense them differently because we may be seeing or sensing them in different environments and with different degrees of adaptation. Most scientists don't worry about calibrating their senses because they use instruments which can measure physical events in an objective, non-adapting manner. That's why most scientists have labs, have equipment, and need budgets. When you take a chemistry or a physics course on campus, you'll have a lab too, and instruments to detect and record your experiments. But in this telecourse, we don't have a van full of equipment to lug around to measure our physical and natural world. We do have our senses. They are there, effortless to use, portable. If we appreciate and understand their advantages and disadvantages, we can use them for objective scientific observations. And that's just what we'll do. When we want to observe even more, we'll extend our senses with the help of tools and instruments and even helpers with enhanced sensory talents. Scientists and engineers develop tools and instruments to make objective observations and measurements about the natural world, to help us extend our senses and to substitute for our senses where they are inadequate for objective measurement. We'll deal with some of those tools later. So what's our bottom line? Well, we observe, but we perceive. We receive only a small part of the information available. We observe the natural world via our senses, but our perception of that natural world is based on personal experiences, attitudes, and other factors. Our senses mainly respond to changes in dynamic events. Our senses adapt, accommodate to different situations. Our senses work together. We use sensory integration to develop our perception of the natural world. Although our senses are versatile, sensitive, portable, and very useful, our perception of the world is often not fully objective or reproducible. The final bottom line is we have to understand, control, calibrate our senses to make the objective observations needed in this course. That's all for this program. Until next time, keep your eyes and ears open, be alert, observe, perceive, and enjoy interacting with that wonderful world around you.
Listening to you, I get the music. Gazing at you, I get the heat. Following you, I climb the mountain. I get excitement at your feet. Right behind you, I see the millions. On you, I see the glory. From you, I get opinions. From you, I get the story. Listening to you, I get the music. Gazing at you, I get the heat. Following you, I climb the mountain. I get excitement at your feet. Right behind you, I see the millions. On you, I see the glory. From you, I get opinions. From you, I get the story.